Hey everyone, today we're going to take a look at carbon. Carbon is amazing because of the truly vast number of different forms it can take. Pencils, jewellery, nuclear reactors, supercars and bikes. They all have this one super versatile element in common. But how can carbon do all this, and why is carbon so important in nanoscience? Let's start by looking at the periodic table. Carbon appears here. It is the sixth element, which means that it has 6 protons in its nucleus and 6 electrons orbiting around it. One way of thinking about an atom is like this. The nucleus is a bit like a planet, and the electrons orbit around it like a set of moons. The electrons fall into different orbits, and each orbit holds a different number of electrons. The first orbit has 2, the second has 2, and the third holds up to 6. However, in the case of carbon, the third orbit only has 2 electrons in it, as there is a total of 6 electrons in each atom. Now, atoms are most stable when the orbits are full. For carbon, this means each atom has to share electrons with 4 more atoms to be the most stable. In other words, carbon atoms can form 4 bonds when assembling into molecules. Bonding between carbon atoms can take one of 3 different forms, each of which leads to a material with radically different properties. sp3 bonding, as it's called, gives rise to the structure we all know as diamond. Each carbon atom sits at the centre of a tetrahedron, and is bonded to 4 others at the apices. Diamond is one of the best electrical and thermal insulators that exists, and is incredibly hard. It's used to make hard-wearing drill bits and tools, as well as being set in lots of different jewellery. sp2 bonding, on the other hand, produces flat sheets of carbon arranged in hexagons. This is graphene. In contrast to diamond, graphene is one of the most electrically and thermally conducting materials ever discovered, and it's very transparent. If lots of sheets of graphene are stacked together, you get a much more familiar material, silvery graphite. Just as you would find in pencils or nuclear reactors. Graphite is very soft, because the individual graphene sheets can slide past each other very easily. If, however, you take a strip of graphene and roll it up, you get a carbon nanotube. Carbon nanotubes share many of graphene's amazing properties. They can conduct electricity and heat, but are also incredibly strong. What's unusual, however, is that depending on the direction you roll them up, you can produce metallic or semiconducting types. So some are useful for making wires, and others are good for making transistors. sp bonding is found in linear molecules like acetylene, and is also known as a triple bond. This is because each carbon atom shares 3 electrons with its direct neighbour. An all-carbon material consisting of only sp bonding is called carbine, or polyion carbon. Such materials are almost impossible to synthesize, and to date people have only really been able to study them when they're trapped inside carbon nanotubes. There are other situations that exist in between these 3 standard cases too. For example, materials which are a mixture of sp2 and sp3 carbon atoms have very similar molecular structures to glass, and so are called glassy carbons. Materials like the activated carbon in water purifiers have this kind of structure at the atomic level. A class of carbon where the atoms assemble into balls are referred to as fullerenes. The most famous one, Buckminster fullerene, is composed of 60 carbon atoms arranged in hexagons and pentagons, just like the seams of a football. This strange form of carbon has been detected in many different places, from soot to dust clouds in deep space. The fullerene family includes some even more bizarre structures, like nano-onions and nano-horns. So as you can see, elemental carbon exists all around us, in a plethora of weird and wonderful forms. In future episodes, I'll be discussing some of them in more depth, including how we can make them, and how we can use them to build new and interesting stuff. See you next time! Thanks for watching, everyone. If you like what I do, please consider supporting my work via my Patreon page, where you'll have access to a range of in-depth discussions on the physics, chemistry and engineering of nanomaterials. If you'd like regular updates, please subscribe and like the video. It helps so much, and I look forward to talking to you again soon.